Welcome to this presentation of the Annual or Condition Inspection Powerplant. My name is Tim Guerrero. I'm the Airframe and Powerplant Program Director at Westwood College of Aviation Technology in Denver, Colorado. One of the school's senior powerplant instructors, Vaughn Dowell, and myself will present the basic skills and techniques necessary to perform an annual inspection on a Lycoming engine installed on a Piper Archer aircraft.
The inspection begins with a search for airworthiness directives on the FAA website. The FAA database provides detailed information concerning each airworthiness directive and identifies precisely which aircraft or components are affected. Note that some ADs only cover specific serial numbers or dates of manufacture. Also note that some ADs require yearly compliance, needing to be redone and relogged each year.
All airworthiness directives that apply to your airframe, engine, propeller, or appliance must be complied with before the aircraft can be returned to service.
If an airworthiness directive does require action, then add it to your checklist.
The most important tool to begin any inspection is a checklist. Checklists are available from the airframe or engine manufacturer, and if not, a generic checklist is available in FAR Part 43.
It is essential that the checklist is completed accurately and thoroughly, as it becomes part of the legal record of the airplane. Assuming no known problems dictate otherwise, the next step is to fly the airplane. We do this for two reasons. First, to become familiar with the operating condition of the engine, and second, because tasks such as the compression check and oil change are best done with the engine as close to operating temperatures as possible. If you are qualified and have permission, you may be able to conduct this flight on your own. If not, take the right seat while the owner takes you on a 15-minute flight. If this is still not possible, at least run the aircraft on the ground until the oil reaches operating temperature. Pay close attention to the sound and feel of the engine. Take notes of key instrument indications during the run-up and in flight. These observations will serve as a benchmark for the post-inspection flight and may also provide indications of problems which need to be addressed. As in any standard run-up, there are certain key indicators to look for. Check oil pressure, fuel pressure, and that full power is maintained at maximum RPM. Perform a Magneto Check, noting that as each mag is switched off, there should be a maximum drop of 120 RPM and no interruption in engine smoothness. Check for a slight RPM drop when carburetor heat is applied. Throttle movement over the full range should give a smooth transition from a steady idle to maximum RPM. Once in flight, make note of anything which might seem abnormal to the running of this engine. Check for proper indications of the cylinder head and exhaust gas temperature gauges, and check once more for steady readings of all engine gauges, especially the fuel and oil pressure gauges. With the plane in the hangar, the full cowl is now removed and set aside for later inspection. The engine is then cleaned of any oil, grease, or other debris that could hinder a proper inspection of the engine.
The compression check is probably one of the best indicators to actually tell how an engine is running. It is also one of the most dangerous procedures that can be performed in aircraft maintenance. The manufacturer's service bulletins or service letters, as well as AC 4313, both require the engine be brought to operating temperature prior to accomplishing a compression check.
Start by removing the harness connectors and then the upper spark plugs from each cylinder. Remove the harness connectors from the bottom plugs to prevent accidental firing, which could occur if a mag switch were not properly grounded. As each plug is removed, it is numbered with a felt tip pen to identify its cylinder and position, and then placed in a spark plug tray with the firing end up. Now turn the engine in its normal direction until cylinder number 1 is on its upstroke near top dead center. You can judge this by placing your finger over the spark plug hole while turning the prop. When you feel and hear air pressure escaping, the piston is on its upward stroke. Continue turning until you hear the impulse coupling in the left magneto snap. When it does, you're at top dead center. On many direct drive aircraft, the position of top dead center is also marked on the ring gear. When this mark is aligned with a corresponding mark on the engine starter housing, you are also at top dead center on the number 1 cylinder. With the cylinder at or slightly before top dead center, screw the compression tester fitting into the spark plug hole. Connect the compression tester to an air supply of at least 100 psi. Connect the tester to the cylinder. Now, with someone firmly holding the prop in place, slowly turn the output valve until 80 pounds of pressure are entering the cylinder. With pressure applied, observe the right side indicator and read the maximum pressure shown. On a healthy engine, that will be between 70 and 80 pounds. Have your assistant lightly rock the prop back and forth. This will help seat the rings, thus more accurately mimicking the engine's actual operating condition. Once you have your best reading, reduce pressure from the air supply, and once reduced, your assistant can then release the prop. This process is then repeated with each of the other cylinders in the actual firing order of the engine. As each cylinder's compression figure is taken, the value is logged as a figure over 80.
The readings resulting from this compression check must be compared with AC 4313 or the manufacturer's service bulletins or service letters. AC 4313 states any reading below maximum of 25% or an actual reading of 60 over 80 must be corrected immediately. But please remember that in all cases, the manufacturer's service bulletins and service letters will supersede AC 4313.
If your compression is low, it may be possible to determine the source of a leak by listening for escaping air while the cylinder is pressurized. If seepage is heard through the exhaust pipes, the problem is likely to be a poorly seated exhaust valve. If heard through the carburetor, the problem is an intake valve. If through the oil dipstick tube, then air is leaking past the piston rings, indicating worn rings or a scuffed cylinder wall.
The inspection requires the checking of oil filter or oil filters that might be on your engine, and it is also an opportune time to drain your engine oil. Remember that when you decide to change your engine oil, please have your engine up to operating temperatures. Warm oil will carry more of the contaminants out of the engine crankcase.
Draining of the oil is done through a drain port located at the lowest point on the engine sump. Some older models have a solid plug which is removed with a box wrench. However, most engines are equipped with a quick drain fitting as shown here, which is opened by hand. If you plan to send a sample of oil for spectroscopic analysis, it's best to pour that sample beginning 5 to 10 seconds after the oil starts to drain. To prevent contamination, let it pour directly into the provided container. When the oil is finished draining, close the plug. Check the security of the safety wire and the plug itself. Examine the plug for any sign of leaking. If you do suspect a leak, remove the plug and inspect the O-ring, which may need cleaning or replacing. Now to the oil filter. Remove the safety wire, tightening the filter to the engine. Then, with a wrench, unscrew the filter a half a turn. Before unscrewing the filter the rest of the way, a trick of the trade is to use a metal punch and tap a hole through the top of the filter wall. Now unscrew the filter another half turn, allowing the oil in the filter to pour into a small container. This beats oil spilling all over the engine compartment as the filter is removed. With the oil in the filter drained, the container can be removed. Keep some rags at hand as there will still be some dripping from the hole and filter flange. Prior to installing the new filter, dab some oil on its rubber gasket. Remove the old filter. Screw the new filter on by hand. Tighten the new filter until the rubber gasket begins to compress. Then with a torque wrench, tighten to manufacturer's specifications. Now re-safety wire the filter from one of its metal tabs to a point on the engine or engine mount. Inspection of the inner filter element for trapped metal particles is standard procedure. This inexpensive filter cutter tool does the job quickly and easily. A utility knife should then be used to separate the filter element from its metal housing. With the element removed and unraveled, inspect with a flashlight and magnet. A few specks of material do not represent a problem, especially with a new or newly overhauled engine. However, if your filter element is coated with metallic debris, further work is needed as these particles represent a condition which could soon cause a major engine failure. The oil finger screen, normally located at the bottom of the engine, should also be checked for large pieces of debris. If it is clean, it is simply reinstalled. If pieces of metal are found, the source of this material must be found and corrected before your next flight. You can now refill with fresh oil up to the manufacturer's specs. Remember that once you start the engine, about a quart of oil will circulate into the new filter, so fill accordingly. The final item in the oil system is the oil cooler along with its hoses and fittings. If the oil temps noted on your pre-inspection flight are normal, then the inspection can be limited to a visual check of the surface of the cooler and removal of any dirt or debris within the cooler's fins. Any present must be cleaned out either by hand or with compressed air. The cooler's mounting brackets are checked for damage and cracking, and all related lines and fittings are checked for security for the absence of any signs of leaking. The engine's vent line is checked for security and that it is clear and free of obstructions. Typically, the line will protrude slightly below the cowl. Be sure it is held firmly in this position.
The ignition system consists of the magnetos, harnesses, spark plugs, and the ignition switch. Proper operation of all of these components is critical to safe engine operation.
The spark plug harness fittings are removed with two open-ended wrenches, one to actually loosen the fitting and another to hold the upper nut from turning so as not to twist and damage the harness wire itself. It is important to remove the harness connector cleanly. Dragging the tip against the plug can damage the tip and impair its functionality. The plugs are then removed with an aircraft-type spark plug socket. Aircraft spark plugs are extremely fragile, so be careful and do not let one drop. If one should be dropped, it must be discarded. Even if damage is not evident, it is almost certainly there. Fortunately, aircraft spark plug sockets are magnetized, which helps prevent the chances of this happening. The removed plug is then numbered with a felt tip pen to identify which cylinder and position it came from, and then placed in a spark plug tray with its firing end up. There are 4 steps to servicing your spark plugs: visual inspection, cleaning, setting the gap, and testing. A visual inspection of the plug head reveals a great deal about the operating condition of your engine. A light deposit of dull brown material on the insulator and minimum buildup in the firing cavity indicates a healthy combustion process. Black sooty deposits indicate carbon fouling, which potentially has several causes, but is most likely caused by either the pilot's insufficient leaning techniques or a leaky primer. Wet oil on the plug face is typically caused by worn piston rings or valve guides. These problems may also have been revealed during the compression check. If severe enough, extensive engine work may be required, or possibly even cylinder replacement. If the firing cavity is filled with hard bead-like deposits, then lead fouling is occurring. Typical causes are poor fuel vaporization, low cylinder head temperatures, or plugs with an improper heat range for your engine. Whatever the case, it must be investigated and corrected. Now look at the shape of the insulator head. Normal use will wear the head to a football-like shape. Roughly speaking, if the width of the electrode has worn to less than half its length, the plug is beyond its service life and must be replaced. For a more precise measurement, this erosion gauge, Champion part number 482, provides an easy calibration. For any given gap value, if it fits in the hole, it's worn past service and must be replaced. If it doesn't, it's still a good plug. The ceramic insulator inside the firing cavity is then checked for cracking. If there is even the slightest sign of damage, the plug must be replaced. The plugs are first chemically cleaned by immersing them in a small container of Stoddard solvent for 10 to 15 minutes. This will remove grease and other soft deposits from the outside and within the firing cavity. Once degreased, the plug can be dried with compressed air. Remaining clumps of material should be chipped out with a hand-held pick tool. Final cleaning and function testing is done with a grit blasting cleaner and tester tool. Be aware of the type of abrasive used in the blaster. Silicon types can contribute to future plug fouling and should not be used. Press the plug into the rubber adapter in the cleaning hole and turn the plug in a circular motion while cleaning. Operate the blaster only for a few seconds. After blasting, blow out any traces of grit with compressed air.
Now that the inspection is completed, we know which spark plugs can be reused and which spark plugs need to be replaced. Remember that all spark plugs need to have the gap checked and then retested prior to installation.
The existing gap is measured and, if necessary, adjusted to specification noted in the engine's manual. The standard procedure to confirm any gap is that a smaller wire would pass right through, while the next largest size would be too big to pass. If the gap is too large, the electrode may be pushed inwards to reduce the gap. This is done very carefully with an aircraft-type tool which holds the plug and slowly turns an arm, pushing the electrodes inwards. Do this in small steps, being very careful not to close the gap too much, as any attempt to reopen it will almost certainly destroy the plug. Do not leave the gauge in the plug while making adjustments. This can cause the wire to be pushed into the electrode and crack the insulator. On a fine wire plug, this process is somewhat easier. However, extreme care must be taken, as these electrodes tend to be brittle and will break easily. The plug is brought back to the tester and placed into the function test socket. This test sends high voltage through the plug and produces a strong blue arc in a sight window, showing that the plug is indeed capable of transferring the high voltage from the magnetos into a strong and usable spark. Re-inspect once more with a magnifying glass to be sure that all debris has been removed and the plug is indeed suitable for another year of use. Rotating plug positions significantly increases their service life. This is because as the magneto fires consecutive cylinders, it switches with each pulse from positive to negative polarity. So on an engine with an even number of cylinders, each plug is always fired in the same direction, causing it to wear more quickly. each plug is moved one step forward in the firing order and switched between top and bottom. Because the copper gasket between the plug and cylinder will work harden with use, it's recommended that these be replaced every time you remove a plug. New gaskets are cheap insurance against leaking combustion gases. A small amount of anti-seize compound should be applied to the plug beginning near the second thread from the end, being careful not to get any on the firing tip of the plug, as that would immediately cause the plug to short out. Screw the plug in hand tight, and then with a torque wrench, tighten it down to the proper factory specification. The harness inspection starts with a visual check of the cables themselves, paying particular attention to the tips of the cable fittings. Look for fraying or burn marks in the wire, especially at points where they may be chafing against other wires or passing through baffles. Check the security of the cables at routing points to the engine, and also into the back of the magneto. Next, we perform a functional test using a high-voltage continuity tester. The first red lead is attached to the metal spring on the connector fitting. The second to a power source, in this case the starter solenoid on the firewall. And the black ground lead is attached to a suitable ground point on the engine. Push the test button and you should see a strong and steady electric arc in the tester's view window. Do be careful around these leads. This tester carries 15,000 volts, enough to cause serious injury. Next, the magnetos. The magneto case should be carefully inspected for any signs of cracking or corrosion. Cracking can occasionally be found in the area of the mounting flange. This is an example of a magneto with a cracked flange, which is obviously not airworthy and must be discarded. The vents in the magneto case are checked to be sure they are not clogged. Clogged vents can trap gases, causing corrosion to internal parts. To check the timing of a magneto to the engine, you will need a dual timing light, such as this one. First, check the engine nameplate to confirm the correct spark advance for your engine. In this case, 25 degrees before top dead center is indicated. Turn the engine so that the correct mark on the ring gear aligns perfectly with a small indentation found on the face of the starter housing. Now connect the left and right leads on the timing light to the P leads on the magnetos. Connect the ground wire to a ground point on the engine and turn the ignition switch to both. With the switch on, remember that you're working with a hot engine, so once again it's essential that at least the upper harnesses and plugs be removed before continuing. Now move the propeller back a few inches and then slowly tap it forward until both lights on the indicator come on and the audible tone changes pitch. You are looking for two things. First, that both magnetos open at practically the same time. Second, that the place where they open is very close to the specified mark on your ring gear, showing that they are in fact opening at the correct 25-degree point. The final check of the magnetos is a visual inspection of the P-leads and their connection to the magneto. Simply make sure there are no signs of chafing or fraying to the wire, and then give the wire a slight pull to ensure that it and the connector are firmly attached. With the ignition timing completed, ensure that the mag switch is turned off.
The electrical components use power created by the generator or alternator and stored in the battery. The heat generated by the engine, combined with the vibration inside the engine compartment, makes inspection of these components absolutely critical.
The attachment of the starter motor to the engine is checked by simply grasping the starter itself and ensuring that it is firmly attached. Each of the 4 mounting bolts is checked for tightness. The main electrical lead going into the starter is checked for security, electrical arcing, corrosion, and other obvious faults. The starter ring is checked for missing or broken teeth. As this involves turning the prop, be sure the mag switch is turned off. You should still observe caution in case an errant connection causes the engine to misfire while being turned. Next is the alternator and the alternator belt. The belt is checked for proper tension and the condition of its contacting surfaces. This can be done with the belt in place simply by rotating the prop to expose sections of the belt at a time between the pulleys. The inner surface should feel soft, pliable, and free of damage. A hardened sheen may be due to friction heat from slippage on the pulleys. Such a belt will no longer grasp well and should be replaced. Belt tension should be checked to allow approximately 1/4 inch of play in each direction. If there is too much or too little play in the belt, then the position of the alternator must be adjusted. To adjust the alternator position, first loosen the retaining bolt and then pull the alternator into the correct position. After checking for correct tension, retighten the retaining nut. Be careful not to over-tighten the belt, as this could cause damage to the alternator bearings. Be sure that the safety wire is replaced correctly, securing the tension bolt to its bracket. The electrical connections on the back of the alternator should be securely attached with no signs of burns or corrosion. The alternator attach points and brackets are checked for security and cracking, as is the mounting area on the engine case itself. As the alternator is subject to significant vibrations, cracking in this area is not uncommon. Finally, check the overall security of the mounting by grasping the alternator and ensuring no unwanted movement is observed. The starter solenoid, typically located on the firewall, should also be checked for security and vibration-induced cracking, both in the device itself and around its mounting area. All wire connections to and from the solenoid are also checked for security and electrical burning. All other runs of wire in the engine compartment are checked for security, proper support, chafing, or signs of electrical arcing. The tachometer drive system is simply checked for security and any signs of damage.
No leak on an aircraft should be ignored. Fuel leaks and hydraulic leaks demand immediate attention. Small oil leaks on the engine, especially on older engines or radial engines, are quite common and should be carefully monitored. Larger oil leaks should be corrected at the source.
The check for fluid leaks begins with an inspection of the lower cowl. Telltale staining will immediately tell you what is leaking, how badly, and will give clues to its source. This cowl shows a small amount of oil behind an air intake. This amount of staining is not uncommon, but still should be cleaned and noted so we have a good base for the next inspection. Any size fuel leak demands immediate attention. Carefully check all fuel lines, drain plugs, gaskelators, and fittings for any signs of leaking. To verify the source of a fuel leak, switch on the electric boost pump to pressurize the system, and with it running, recheck all suspected lines and fittings. With the system pressurized by the boost pump, any source of fuel leaks will quickly become evident. Pressurize the primer system to check its lines and fittings and those into each cylinder. Due to engine vibration, primer system leaks are not uncommon. If a fuel leak is found from a fitting, you can attempt to correct it by retightening the fitting, or if it appears to be from an accessory such as a pump or gascolator, replacing the faulty part. Signs of small oil leaks are not uncommon. However, the changing flow of air inside the cowl will often make the source of the leak difficult to find. Some areas to check include the oil filter, particularly if it has not been tightened properly, oil hose fittings, the valve covers, the dipstick joint into the crankcase, and the seams of the case itself. If a leak appears to be coming from the seams of the case halves, do not try to simply tighten the case bolts. Torquing beyond manufacturer's specs could easily crack the brittle case, causing problems far more severe than a small leak. A reddish oily stain indicates hydraulic fluid leaks and most likely a low level in the fluid reservoir. Typically, these systems are covered during the airframe segment of an inspection, but while you're noticing the stain, this would be a good time to check the associated components and then check and top off the fluid reservoir.
Many aircraft today still use the standard updraft flow carburetor, ensuring unobstructed fuel flow, checking the carburetor for security of mounting, the cleanliness of the fuel screen, and the freedom of movement and security of the linkages are all critical to satisfactory operation. A leak in the air induction system prior to the carburetor can result in insufficient airflow to the engine, especially at altitude. A leak in the air induction system after the carburetor is especially hard to detect and can result in additional air being sucked into the induction system, resulting in a leaner mixture. As most pilots know, ice can form in the carburetor air inlet at temperatures as high as 90 degrees Fahrenheit. Proper operation of the carburetor heat or alternate air doors is critical to safe engine operation.
With the fuel selector valve in the cockpit turned to the off position, begin by removing the main fuel line. Then by removing the main inlet fitting from the carburetor itself. With this fitting removed, the fuel screen can be carefully pulled out. The screen is inspected for damage, dirt, or debris and can then be cleaned in solvent. If the screen appears dented, it can often be repaired by inserting a screwdriver and from the inside rolling it back and forth into shape on the palm of your hand. The next step is to check the fuel in the float bowl for sediment. Open the drain plug and collect as much fuel as possible into a clean container. The drained fuel will probably be clean. However, if debris is found, its source will need to be located and corrected. Before replacing the plug, its threads should be coated with an aviation-approved thread sealant. Do not use Teflon tape as a fuel sealant. The plug is then reinstalled, tightened, and re-safety wired to the carburetor. Any remote fuel filters or gascolators should be inspected and serviced. Gascolator service starts with removing the bowl and inspecting it carefully for damage or sediment. The screen filter is then carefully removed from the upper gascolator housing. The filter is then examined and replaced if necessary. Now, with everything reinstalled, turn the fuel selector valve back to either tank and turn on the electric fuel boost pump for a few seconds. With the system pressurized, check again for leaks. If all stays dry, this step is done. The next step is to check the carburetor's physical attachment to the engine and to make sure there are no signs of leaks or cracking. Then, with a half-inch wrench, check the 4 upper mounting nuts for security. The bolts and safety tabs attaching the float bowl to the carburetor body can also be checked for damage and security, along with the carburetor's attachment to the intake air box below. The air induction port, or air box, is also visually inspected, especially around the edges, attach points, and around any seams. Note that this inlet duct was found with a small dent in need of repair. The alternate air system, or carburetor heat door, is checked for security and freedom of movement. The rubber baffling around the inlet door should also be checked to be sure it is in good condition, free of major cracks. You should also ensure that it will properly seal incoming air into the system. If you have an air filter, it is now removed, inspected, and either cleaned or replaced. Paper and foam filters are typically replaced, while cloth filters are usually cleaned in solvent and gently blown out from behind with compressed air. The foam filter on this airplane was determined to be acceptable for use in another 100 hours of service. The final step on the fuel-air system is a check of the throttle and mixture controls on the carburetor, along with their associated bracketry. Each control should move freely and easily from stop to stop, with no indication of binding in either direction. The stop pin on the mixture control should be checked for security. Check for the presence and security of cotter pins and other safety devices at the points where the linkage fittings attach to the carburetor control arms.
Inspection of the cooling system simply involves the ensuring of unobstructed and properly directed airflow through the engine inlet, through the cylinder fins, and out the engine cowling at the bottom. Any debris in the engine cylinder fins, twigs, mud, etc., must be removed.
Start by checking the integrity and security of the baffles that deflect the incoming air onto the top of the cylinders. Misformed or damaged baffles will allow the cooling air to leak away from the engine, resulting in overheating. The rubber sealing material should be checked for cracks and other damage. It should be firmly attached to the metal housing. The rubber baffle should bend slightly inwards and be pliable enough to form a good seal with the upper cowl, so as to direct the cool air down through the cylinders. The security of the attachment of the metal baffle should be checked, and the metal itself should be examined for cracks or any other defects. Then check between the cylinders to make sure there is no debris which can block or disrupt the airflow, and check the condition of each cylinder's cooling fins for cracked or missing segments. If damage is found, check with the engine manufacturer to be sure the damage is within prescribed limits.
Inspection of the exhaust system involves a visual check of all exhaust system components and, of course, a hydrostatic or pressure check of the entire system.
The visual inspection of the exhaust system starts at the exhaust port of each cylinder head. Inspect each junction and its gasket for any sign of cracking or leakage. Pay particular attention near any welded joints, as these areas are particularly susceptible. An exhaust leak would be seen as burn marks or a plume-shaped discoloration downstream of the leak. The point at which the exhaust gas temperature probe enters the exhaust should be carefully examined, as this is a common source of leaking gases. Leaks are not or near slip joint and are acceptable as long as the leak is small and not closer than 2 inches from a cabin heat exchanger. Check the general security of the exhaust system by taking firm hold and checking for any unusual play. Check the cabin heat control linkage for security and freedom of movement. A pressure check of the exhaust system can be done using a regular shop vac. First, block any secondary openings with an old rag. Then, using duct tape to hold it in place, place the outgoing vacuum hose onto the pipe opening. Switch on the shop vac, and with the system pressurized, apply soapy water around any joints and welds. Any leaks will be apparent by the bubbling soapy water. If you do need to mark a suspect area, use only white chalk. Anything else can scratch the pipes, causing hot spots in the metal and future failure points. With the pressure check complete, do remember to remove any rags you used to block exhaust ports. Scratches are a potential source of weakness in the exhaust system, and if any are discovered, they should be removed using fine emery paper. 400 grit is ideal. A good further reference is FAA Advisory Circular AC 43.13, Section 1B, which shows good examples of common exhaust system leaks. And finally, inside the cabin, replace or install a fresh carbon monoxide detector card.
The engine mount consists of a welded structure, 4 heavy shock mounts, and the firewall. Both the mount and the firewall are under constant stress and vibrations in flight and must be inspected carefully during each annual inspection.
Each welded joint of the engine mount assembly should be carefully inspected for any signs of cracking, corrosion, or rust. This is especially important in areas where a nose gear or main landing gear sockets are incorporated as part of the assembly. Each tube should be checked for straightness by aligning a straight edge along its side. Any deformity will easily be seen. The rubber shock mounts that attach to the engine are checked for tightness, security, and other deformities. If any of the bolts are found to be loose, they must be carefully retorqued to manufacturer's specifications. Each of the mounts should appear to be holding its symmetrical shape. If one side of the donut appears compressed or deformed, or if the engine appears to be sagging, then the shock mounts should be replaced. The firewall in the areas where the engine mount attaches is subject to the same stresses as the mount itself and should be inspected for signs of damage. Check each penetration for security and for a good seal. Be alert for any sign of chafing on wires or cables where they pass through the steel firewall. A small suspected leak area can often be corrected by applying a generous amount of high-temperature silicone all around the opening. Next is an inspection of the engine cowl. Both the top and bottom sections are gone over for cracks, dents, chafed out areas, and any other signs of deformation. Any access doors, such as for the oil dipstick, should be checked for security and freedom of movement. Attention is given to hinge lines and the cowl's attachment hardware. Carefully check each fastener and the area on the cowl around where each fastener connects. The inside of the cowl is now given a final cleaning with acetone and a Scotch-Brite pad as preparation for your next inspection.
The propeller is probably under more stress during normal engine operation than any other engine component. Proper inspection of the propeller during an annual inspection is critical. A propeller that's improperly torqued or even slightly out of balance can result in a cracked hub or a damaged propeller flange.
A fixed-pitched metal prop is inspected visually and by feel for dings, cracks, and any other signs of damage. If any cracking is present, the prop must be taken out of service. The same is true for large gouges. However, small dings may often be removed by lightly filing the affected area. Be sure to remove a similar amount of material from each blade of the propeller in order to keep it balanced. The propeller is then finished by smoothing out the file marks with fine-grade emery paper. A wooden propeller is inspected in much the same way, except that you have a little more freedom to sand out small gouges on the leading and trailing edges. Besides cracking, a wood prop is also checked for signs of delamination or for worn varnish, which can allow moisture to seep into the wood. If large gouges or extensive wear is found, the prop should be sent to a certified propeller shop for repair and rebalancing. In the event that any specific airworthiness directive or service bulletin requires the removal of your propeller as part of the inspection, before removal, its position on the hub should be noted and marked. It is important that when the prop is replaced, it is put back in the same position as it was prior to removal. On both wood and metal props, the hub, especially around each of the bolt holes, is checked for cracking or corrosion. The blades of a constant speed prop are inspected in the same way as a fixed metal prop. The security of the blades can be checked by grasping each blade at its root and attempting to twist it in the hub. If you feel play, further attention is required. The hub itself is then checked for signs of physical damage or for oil or grease leaks from its seals or breather holes. Re-greasing of the blades inside the hub is done through the Zerk fittings on the hub. With the opposing Zerk fitting removed to prevent overpressurizing the hub, apply grease to each remaining Zerk fitting. Replace the removed fitting and clean off any excess grease. Replace the Zerk caps, and you're done. The FAA requires the following checks before the aircraft can be returned to service: full power RPM, idle RPM, Magneto Check, RPM drop within acceptable limits, oil pressure, oil temperature, cylinder temperature if equipped with a CHT gauge. These checks can legally be performed on the ground, but we'll go the step further and continue the operational check in the air. This will better ensure that you successfully corrected any problems encountered in your pre-inspection flight. The flight is conducted in the same way as in the pre-inspection, noting the general feel of the airplane, and by rechecking the instrument readings taken before. This is also a good opportunity to discuss with the customer the work that you've done and answer any of his or her questions. Your customer will appreciate your interest and remember it and you the next time around. To legally return an aircraft to service, a notation in the aircraft's log must be made certifying that the inspection was completed, along with a record of compliance if the completion of an AD was included in the work. The basic statement is written as, I certify that this aircraft has been inspected in accordance with a 100-hour or annual inspection and was determined to be in airworthy condition. For a home-built aircraft inspected by the person holding a repairman's certificate, the log entry is, I certify that this aircraft was inspected on what date in accordance with the scope and detail of Appendix D of FAR Part 43 and is found to be in a condition for safe flight. Any work done aside from the actual inspection is also logged. This is followed by the signature and certificate number of the person returning the aircraft to service, typically a mechanic with inspection authorization.
If further problems or questions arise, or if any defects are detected, please consult an experienced airframe and powerplant technician.
The purpose of safety wiring is to hold a bolt or some other threaded component in its torqued position so it cannot work itself loose. Safety wire comes in several materials and thicknesses. Stainless steel is most common. Thicknesses range from 20 thousandths to 62 thousandths of an inch, with .032 being the most common. As a general rule, use a wire thickness of 1/2 to 3/4 the diameter of the hole of the bolt to be secured. A safety wire tool is a type of locking pliers set on a twisting rod. Both ends of the wire are locked into the pliers' jaws. Pulling the center post twists the two ends of wire tight together. Insert the wire through the hole in the bolt's head. Then wrap the end of the safety wire around the head of the bolt in a tightening, normally clockwise direction, towards the attachment point. Just past the attachment point, lock both ends of the wire into the jaws of the safety wire pliers. Pulling on the central post will then twist the wires together. Twists may need to be added or removed by hand to ensure that the wire is tight and twisted throughout the entire run. The wire is then secured to the attachment point, here a second bolt head. The ends are then placed into the safety wire pliers and twisted together. The wire is then cut, leaving a tail of 1/4 to 1/2 inch, which is folded inwards to secure it and prevent snagging. Twists should be tight and even with 6 to 8 twists per inch. Propeller bolts are a typical and important safety wire installation. They are normally wired together in pairs. When safety wiring closely spaced bolts, the number that can be safely wired with a 24-inch length of wire is the maximum permitted in a series. This installation clearly illustrates the principle that safety wire should always be applied so that all pull exerted by the wire will tend to tighten rather than loosen each bolt. The alternator tension bolt provides a good example of safety wiring a fastener to a fixed object rather than another bolt. The procedures involved are essentially the same. The wire is inserted through the tension bolt head, twisted tight with the safety wire pliers, and then secured to the alternator mounting bracket. Safety wiring is not confined to fasteners but may be used with any threaded component. Here we show it being used to secure an oil filter to ensure that it does not come loose during flight. Again, the principles and procedures involved are essentially the same. The longer runs of wire that are often necessary when securing components such as the oil filter make achieving correct tension all the more critical. The wire should not be under so much tension that normal handling or vibration will break it. More information on safety wiring can be found in FAA Advisory Circular 4313, beginning on page 7-19. We'd like to thank the instructional staff at the Westwood College of Aviation Denver campus for their gracious cooperation and oversight in creating this presentation.